In today's lecture, we're going to look at water's life-supporting properties. So it's got some pretty cool properties that are just unique to water. Well, not necessarily unique to them, but it's the combination of all these different properties that make water unique. So we're going to start off with two essential questions today. So we'll get our EQs going. The first one that we want to look at is, what about water's chemistry? Rather, what about the chemistry of water? It makes it so essential to life. There we go. Because that's what we're trying to answer. What are the cool properties that make it so essential to life? The second thing is very short. What is pH? Okay. Hopefully you can already answer that question. Hopefully we've covered that one at least at some point in time. But nonetheless, there you go. So some of the cool properties of water is they have a tendency to stick together, and the same kind of molecules to stick together. The simple way to put cohesion is it sticks to self. Water molecules like to stick together. So cohesion is stronger for water than for all kinds of other liquids. And you know that it's cohesive and has cohesion because when you look and you put a little droplet of water on like a table, it's rounded like that. That's all these water molecules kind of sticking into each other. They're just trying to stick together. They're like huddling in a little ball. They're trying so hard to stick together. Plants actually depend on that cohesive property in order for water to basically defy gravity and to go from the root system all the way up to the leaves. It requires that these water molecules kind of be able to pull each other up. It's like somebody's hanging off a mountain and one guy's pulling the rope and then pulling the other guy, and he's pulling himself up, but he's also pulling the other guy down below to make sure they both get to safety. That's what water does. It's like the one guy pulling the other guy because they're the same time. We'll have to see if that visual makes any sense to you later. Alright, the tendency for two kinds of molecules to stick together is adhesion. And you think of like tape adheres to something else. The way I like to put this is it sticks to other stuff. So not only is water really good at sticking to itself, but it also sticks to other crap. And if we haven't looked at videos already, making these a little ahead of time, but if we haven't looked at it already, there's some great videos that you could do it. It's like if you see water and you put your finger on it and then you pull your finger up, it's like the water is like sticking to your finger just a little bit. That's adhesion because it's sticking to you. Okay. Cohesion is related to surface tension. And surface tension is just a measure of how difficult is it to break through the surface of a liquid. Okay, and the things that make water have a high surface tension or a high difficulty to break through the surface of it is hydrogen bonds. Any of the cool properties of water is basically probably due to hydrogen bonds. Okay, if you've got questions on this in the future, the answer might, like, why does water do this? It's probably hydrogen bonds. That's just a trick for you. Okay, so it behaves as if it were coated with an invisible film, which actually makes these little dudes, water striders, stand on it easily. And they stand on it without breaking through because they're awesome. And it's cute. Oh, okay. That's a water strider, by the way. I'll come back to it. But here's a look at what happens. We'll look at this video and we'll examine it a little bit later. But as water molecules move up, they'll actually continue to pull each other up. Kind of like water moving through a straw. But as they move up, they're going to kind of stick to the sides to be able to have something to grab onto to pull each other up. So that'll be adhesion and cohesion, and we'll look at it in this video a little bit later. Here's a water strider. Their legs are actually just made so that way they don't break through the surface tension. They just lay their little bodies all spread out across it and they don't fall through. And a side note, they are mean. They bite, they're mean, they're angry, all that good stuff. Thermal energy is the energy associated with the random movement of atoms and molecules. So thermal energy, remember thermal, like the first thing that came to mind was thermostat, but also like a thermometer. Thermometer measures heat. So this has to do with the heat of energy. So energy associated with heat. Let's see. Thermal energy in transfer from a warmer to a cooler body of matter is defined as heat. So it's where molecules move more to where they move sort of less, is kind of what we're getting at. So temperature actually measures the intensity of heat. And the intensity of heat, that's the average speed of the molecules in a body of matter. So we're talking about water. So think about like an ice cube. It's not moving, right? So the speed of those molecules is 0. So it has less heat. If we look at water fluidly, so liquid water, it's fluid. So those molecules are moving more. So they have a greater average speed and thus a bit more heat. Water vapor, we can't even see that stuff because they're all over the place. They're crazy. But they have even more speed. So they've got more heat. So the more you heat water, the more those molecules move. So greater temperature, greater movement or average speed of those molecules. Okay, heat has to be absorbed to break hydrogen bonds. We need heat to break hydrogen bonds because that's associated with it too, is that if ice has more hydrogen bonds than water vapor. It just does. So kind of the movement is also associated with these hydrogen bonds. If we release heat or make something colder, so heat absorbed is making it hotter, that we'll say heating, and heat released is cooling, then we'll form hydrogen bonds. So to raise the temperature of water, hydrogen bonds between water molecules must be broken before the molecules can move faster. Okay, that's it. Because we've got to break bonds before we can make it move faster and heat it up. So when warming up, water absorbs a large amount of heat and then moves more. And when water cools, water molecules slow down, more hydrogen bonds form, and a considerable amount of heat is released. Okay, I'm trying to break it down for you. If it doesn't make sense, come see me. We'll make sense out of it. Okay. Earth has a huge water supply that moderates temperatures, and it helps to keep temperatures within the limits that permit life. Water's resistance to temperature change also stabilizes the ocean temperature because it's resistant to change, and it creates favorable environment for marine life because the kind of ocean temperatures don't change a whole lot. Okay, and this also, if you look at it, you think about it, like maybe geographically, we're in Houston, it's hot all the time, but it's hot all the time. We never really experience a winter where there's a lot of snow and there's ice or whatever. We occasionally do, but not a lot. And that's because we're near the water, and water kind of keeps our temperatures relatively the same. When you go more inland, you get those crazy seasons where you'll start to get kind of really hot. When I lived in Arkansas, more inland, it would still be 100 and something during the summer. But then in the winter time, it'll be, 2 degrees outside. And so we have greater range of temperatures. Okay? Even, you think deserts and those things are more inland. You can have, even within a day, you can have the daytime temperature reach well over 100, and you can have the nighttime temperatures in the negatives. So that's a huge fluctuation. All right. And this is kind of difficult to understand. We'll just talk through it, and if you have questions, we'll talk later. But when a substance evaporates, so like when water evaporates, the surface of that liquid that remains behind will cool down. Because remember, we're evaporating. Think with water, we evaporate the water, and so as those molecules speed up, they're going to take the heat with them. and leave what's behind cool. And so we call that evaporative cooling. This cooling occurs because the molecules with the greatest energy leave the surface. They take that heat with them. We'll kind of say it, take heat with them. And this actually relates to how we sweat. So this is important for sweating. So when you get really hot, because we live in the Houston area, and it's going to happen, okay? When you get really hot, you'll sweat, and it'll help to cool you down. Like this guy. He's just got done with the game, and he's got some serious evaporative cooling happening. His body is efficient, though. Okay? Alright, let's say we're at 10-minute mark, so I would take a break here, pause the video, go take a break, do other things, chunk your notes, write some questions, and then come back. Alright, we're at a break point. I'm gonna take this opportunity to give you guys what I like to call Easter eggs. Back in the day with the DVDs and all that stuff, they used to hide sometimes extra little bonus features in DVDs, and they called them Easter eggs if you ran across them. So that's what I call these things in my videos, if you run across an Easter egg. So, here's my thing, as I've noticed, or I have been told, that the YouTube videos will actually make subtitles, and sometimes these subtitles are wrong. So if you would like an equivalent to 5 extra points, it's 1 point, but it's 5 percentage points on your quiz, then write down whatever it is it's saying that's not what I'm saying, and then give me like a timestamp so I can see it. If something happens and it comes up and it's not school appropriate, just write not school appropriate or school inappropriate and then give me a time. Because I gotta know what's coming up on the bottom of these things. I make them, I don't go back over them, so you have to tell me what some of these things are saying. And if you tell me what's coming out weird from what I'm saying and the time, so I can go there and see it, I will give you points on your quiz. They're usually, by the way, my Easter eggs are usually related to whatever content it is, but because we've talked about that, that's your bonus this time. I want to know what this thing says that I'm saying. Okay? So there you go. Alright. Interesting things about water. Water can actually exist as a gas, a liquid, a solid, and we know that. But it's actually one of the only things, the only substances that can exist as all three of these things naturally. Most things occur in one, maybe two of them, but not all three. But water naturally occurs in all three states. Okay. So water is actually less dense as a solid than it is a liquid. Okay, and I'm going to draw you a goofy picture because I can do that. And again, the answer is hydrogen bonding. That's why. But we already know this to be true. We know that water is less dense as a solid because think about you make yourself a glass of water. You put some ice cubes in it that apparently look like that. And they, for the most part, will float, right? Because they're towards the top. You're just going to have to bear with me. Those are ice cubes in a water glass. But they float to the top. So that must say that ice, kind of the solid version of water, is less dense than liquid water. Which, by the way, is kind of a unique property. Most liquids don't do that. They don't do that. They don't. When they become a solid, they sink. That's just what happens. Okay, but when water freezes, each molecule forms a stable, again, hydrogen bond with its neighbor. So they form that bond. As the ice crystals form, the molecules are less densely packed than in liquid water. So because ice is less dense than water, it floats. Right? But let me show you, the best way is to really show you a picture. So what happens with liquid water, I'll start down here, is that it moves. And we know, we've seen liquid water, it's fluid, it moves. And what basically happens is all of these little water molecules are mingling with each other. It's like they've never met before, and they're like, oh, hello, nice to meet you. And they'll walk up to each other and go, oh, it's nice to meet you. Okay, next person, nice to meet you. And that's what they do, is they just mingle, and they walk around, and they talk to each other, and shake hands, and move on. And I don't know, it's like they have short-term memory loss too, because then they forget that they've met each other, they go back, whatever, but they just keep shaking hands all the time. And they actually get pretty close together when they do that. However, if they're going to be in an ice form, it's like a cryogenic state here, I guess. But they don't sit like this. They actually kind of form a bond and shake hands, and then it's like time freezes, and they're stuck that way. And so they're all in these little bonds, and there's actually nice kind of air pockets like in between them. So they're kind of stuck in this way, and you can see how they're less packed together than they are here in liquid water. And that's what makes it float. Okay? So, see how that works? I've got all kinds of cheesy videos for this crap too. That's what's fun. Alright, a solution. So we're in our next part here. We should be able to finish up quickly, but a solution is a liquid consisting of a uniform mixture of two or more substances. Hopefully that's a review. The solvent is the dissolving agent, or the thing that does the dissolving. In most of the cases we're talking about here, we're talking about water. I always think it's the thing in the greater amount, so it has the greater amount of letters in it than solute. Not my bunch, but you get the idea. The substance that is being dissolved is called the solute. Okay, and any time that you have a solution with water that's included is an aqueous solution, and you can think aqua as water, or even in Spanish, agua as water, so it's still along those same lines, just meaning with water. A solution with water. Water's versatility as a solvent, so that's what water is, a solvent. And most of our examples, we're just looking at water. It results from the polarity of the molecules, and that was from the fact that it has different poles or different charges. Okay? And so because it has different charges, like attracts like for most chemistry, so it will dissolve or be attracted to polar or charged solutes. Okay. And so those tend to dissolve in them, forming an aqueous solution. And I like this when water molecules surround them. Water's a friendly little molecule, and it's like a little welcoming committee. It's so sweet. We'll look at it. So table salt's the example that we'll look at. So what happens is we put in a little piece of salt, and each one of these guys will break apart because they're polar or have charges. And water, being the absolute sweetheart of a welcoming committee that it is, will orient towards that thing most appropriately to give it a nice welcome. So, like chlorine here is a negative, all these positive little hydrogens are going to surround it because they're attracted to each other. And it will say, oh, it's so nice to meet you. We're so glad that you're here. Let's go on over here and talk. I don't know, whatever it is they do. And every positive sodium there is, those negative oxygens will surround it and say, oh, it's so nice to meet you. Come on, come this way. And all of the little pieces will be taken away like that because it's just, water's just so friendly. It just wants to make everything comfortable and give everything hugs. We'll look at that later when we talk about osmosis and diffusion and stuff, and it's just, water's just so friendly. Friendly, friendly little molecule. In liquid water, a small percentage of water molecules break apart into ions. We'll have hydrogen ions as H+, and we'll have hydroxide ions as OH-, and both types are really reactive. A substance that donates hydrogen ions to the solution is called an acid, like hydrochloric acid would break apart for those two, so you get an H+ and a Cl-, so donation of H+ makes it an acid. A base is a substance that reduces the OH, or the hydrogen rather, concentration in a solution. So NaOH is one of those because we're going to reduce the hydrogen by giving it an OH- friend to play with, I guess. Well, they'll come back up and make water, but it's still going to take the hydrogen out of the solution. Little reminder on the pH scale, it describes how acidic or basic a solution is. It ranges from 0 to 14, 0 the most acidic, and 14 the most basic. Okay? And those are both really, really strong. If they're on either end of the scale, they're super, super strong. Okay? Each pH represents a tenfold change in the concentration of H+ in a solution. I won't go into that, but hopefully you learned a bit about that in chemistry. A buffer, these are hard to talk about, but a buffer is really a substance that minimizes changes in pH. So these guys are cool where they can accept hydrogen if there's too much of it, or they can donate hydrogen if there's not enough of it. So they'll do kind of whatever they need to do to ensure that we maintain the right pH in the system, to maintain where we need to be at. So here's our scale again with all kinds of cool things in here. Again, on the low side of the scale is battery acid. On the high end of the scale is oven cleaner, both equally as kind of scary in the system, kind of really strong. Neutral is 7. So, by the way, brackets mean concentration. So that concentration of hydrogen ions is equal to the concentration of hydroxide ions. Because nobody likes to write out concentration all that much, scientists or other, I think scientists, yeah, it had to have been, developed little brackets so they could be really lazy. But it happens, right? An interesting fact is that human blood and tears are actually a little bit basic. We maintain a little basicness in kind of in our bodies. So, you know, avoid the basic jokes, but it's still fun. All right. You can see over here just examples of more hydrogen ions are in the acid solutions. They're equal in a neutral, and you get more OH minus in your basic solutions. Quick thing here, just to get you thinking about it. We avoided kind of the major experiment with this one, but carbon dioxide is the main product of fossil fuel combustion, which is basically what happens in our cars. So when we increase CO2 in the atmosphere, we are linked to global climate change. We're increasing it in the atmosphere. There's some data that shows that this has been an issue, and it's been data for this since I've been in school, so there's like 10 years at least of data. Or more. Alright. Just an interesting thing, about a quarter of the human-generated CO2 is actually absorbed by the oceans. And when CO2 is dissolved in the oceans, it lowers the pH of the ocean in a process known as ocean acidification, because it puts acid into the ocean. And there's a whole series of experiments they did, but basically more CO2 bubbles will lower the pH of the water, which makes it more acidic, and the acid in the water will actually break down coral reefs and other kind of animals. It will break down their shells and kill more things off or make it harder for them to survive. That's an issue. Okay. The emergent properties of water support life on Earth. And that's basically kind of what we look at. We'll look at some other things too. I found a cool video the other day I'll show you guys. When astrobiologists search for signs on other planets, they're looking for water. And NASA actually showed that there might be some evidence that water was once on Mars too. So there might have been life on Mars. And that's it. So that's where we'll end this one. Keep it a little simpler. A little shorter. But if you have any questions about any of this stuff, feel free to shoot me an email or ask questions, whatever it is that you need to do, come to tutoring, whatever we have to do, so we make sure that we understand it. Okay?